There we go. I think that should do it. I believe so. Anyway, hi. Yeah, I'm Solar Moon, independent game developer, creator of Tetra3D, Master Plan. Yeah, I do stuff. Hi. So this stream, what I'd like to do is I'd like to try making a light map, or not a light map, a light volume node. So basically, the way that Tetra3D works currently, let me see here. There we go. Here we go. Okay, sorry that's so so weird. The graphics. I'm working on stuff anyway. Yeah. So basically, what I want to do is I want to try just experimenting and see if I could implement some light volumes for kind of like a very primitive PlayStation 1 esque. What's the word? Global illumination kind of. I feel like I have a general idea of the approach that I want to take. I haven't done any research on it, but I feel like it could work. I'm going to put some lights around so that we can see this actually. Oh, the lights are all weak. Yeah, okay. So we do have this. This does not need to be visible. We'll just hide it. That's fine. So yeah, this is what it normally looks like. Oh, I'm sorry. Hold on. A couple things. One, I'm not sure what's up with that flickering. I don't feel like this has been like this before. Like OBS has been doing this previously. I'm not sure why it's doing it now. But yeah, okay. So let me just focus my thoughts. So let me make this invisible. That. Go here. Run it. Okay. So this is a very simple scene. It's just a three-dimensional building. Very low poly, very low resolution. Yeah, very evocative of the PlayStation 1. So what I wanted to do is basically add some kind of a space that basically objects as they pass through that space will take on the colors of the cells within the zone that the space contains. So it's basically a cube, an AABB. And as objects pass through this space, they can darken or lighten the space, or they can receive the colors as they draw. So that's the concept. It's basically a volume that we can write data to and change, how things look. Let me get some music going before I forget. Let me do a couple things here. Hold on. Yeah, let me get some music going here. Cool. Okay, so what I'm thinking as to how this is going to work is essentially we want to be able to there's a couple of ways we could do this. So for one, let's just make this a little bit more complex. I wonder if I can do... Yo, I didn't know that you could do that. That's so cool. Yeah, very cool. All right. Yeah, okay. So the general idea is here. So this little shape, this building, is a good space, I think, to try our light map out. So the general concept is, I think we're going to make a KD tree. We're going to use KD trees to basically make this space divided into cells, divide this space into cells, then basically get the closest point for each vertex and color the vertex, light the vertex according to the value within that cell. It really should be mixed across the cells, but that's fine, I guess. It's fine. We'll say it's fine. And I originally had an idea to do a light map, which is why you see the name is light map. But I decided to do light volumes because of a light volume is a 3D light map. Like if you take a light volume and then just draw a texture or something on it from, let's say, above, and then project that straight down, it's effectively a light map, right? It's, more or less taking effect across every face the same way, just like you could with a light volume. Is just one-dimensional or two-dimensional rather than three-dimensional. So I'm like, well, let's just go ahead and make it 3D because then we can do stuff with it. So let's see if we can get this to work. So the idea is we want to be able to tell how many cells, what the cell size is. So this is going to be an int, I guess we have X, Y, and Z. We want to know, we want to have a KD tree, which I think we should be able to use this implementation that I found earlier. It seems simple, fairly simple. Implemented in Go. Supports 2D and 3D points. So it should be as simple as just dividing up a space, evenly distributing the points, and then just getting the nearest neighbor to any particular coordinate and seeing if we get it. 3, 1, 5, 0. Yeah, we'll see. We'll see what this looks like. And my main motivation here is just, I think it would be cool. and it's cool to kind of come up with like the concept of what if a PS1 could do kind of more stuff, but without like abandoning what makes it work. So it's still vertex lighting, it's still, you know, what it is, but like how would a PS1 do this if it could? That's kind of the idea. Okay, so let's give this a shot. We're gonna make a new file. Or no, we don't need to make a new file. We just need to do this. I'm not sure if I need to navigate out, but we will. GitHub. And let me just take a look at some other implementations if I can real quick. That's interesting. There's only a few. Flat interval tree. What's an interval tree? And tree will build the tree once, static, no updates after creation. Returns indices to the initial bounds array. Finding all bounds for a single float 64 value. I see. So this is it's, I guess it's essentially like something that finds, I mean, it's not really a tree. It seems like it's basically just like a line, right? And it's just intervals. And so, I mean, that's what it sounds like. That's what it seems like. But I guess if you can use this interface, then maybe you can use multiple bound sets or something. Let me see. Interval tree. Tree of the day structure. Well, maybe we can use this, but I'm more familiar with the KD trees, so maybe I'll try that first. Duplicate coordinate support. Tree construction is larger, 10 times larger for a large inn. is that, let's see. Enlarging. Okay, and it is significantly faster. To 15 times faster. A small in. What is in? Vector.v. Oh, that's going to be a problem. In length vector. I don't like that it forces, like it's working based off of an existing geometry library or framework, since I have my own geometry framework. So we'll stick with this one. We'll stick with this one for now. See what we get. That's good. All right, so let's go ahead and get this. Okay. So no change. Yeah, we have 3D points as well. Okay. Okay. In terms of balanced KD tree. KD tree. Okay. So let's say we have to specify the number of cell divisions. So division count X, or maybe just cell size. Yeah, maybe volume size. Does it make sense to have a dimensions for this? Because yeah, okay. So yeah, the volume dimensions. Then you have the cell size X, cell size Y, and cell size Z. There we go. Okay. And then we'll say LV dot resize. Where we make the tree. We need points. Okay. So we'll put this down here. We're going to pass in the... We don't need it to be a model. It can just be a node. Do we need the dimensions? I guess we will record the dimensions. Like that. that, and then we go over here and we say dimensions. All right. There. Cool. 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 All right, so this is the idea. Let's make sure nothing's going crazy. Okay. Let's divide up this subdivide this map a little bit. Yeah. Cool. All right, so what we want to do is let me think. We want to make a new KD tree. We're going to need points. So something like this. We can remove points. Okay, we can add points, we can remove points, and then we balance. Okay. Rebalances by recreating. I see. Canon. K nearest neighbor. Nearest neighbors. I see. Sort of a distance starting with the nearest. Cool. Okay, this could work pretty well. All right. So what we want to do is we want to make points for each point in the dimension set. So we want to start with Z. I guess it doesn't matter, but we'll start with Z. It'll be dimension.min.z. Z is less than dimension.min.max.z. Z plus equal depth divided by cell size Z. There we go. And then we just do the same thing for Y. And this will be height. And we do the same thing for X. And this will be width. You know what? Let's make another one. Yeah. Cool. So now what we want to do is add a point that is, points. Oh, this is, yeah. Tree points. Points. Yeah, points. Oh, maybe I have to go get, this is strange. For some reason, points doesn't exist. Let's try this. Let's see. Now, let's see. How do I actually store data, though? Okay. I guess if you don't need the data, then this is fine. I do need data. I need to store light levels. So this is instead going to be a point like this. The coordinates are float 64. And it's going to be X, Y, Z. And the data can be a number. It will be a float 32, and it'll be just 0 for now. And then we create a new tree using the tree points. Okay, let's see if this works. Oh, we aren't creating. Yeah. Okay, so we have the light map. We don't actually need that. We can say new light volume from model. We can use this. Let's say maybe we could do this another way, and well, yeah, we'll say that the cells are all the same size. They're all a quarter of a unit large. Let's see, not as nil. Oh yeah, this light volume. Oh yeah, we need a node. Yeah, okay. All right, let's try that. Light volume creation 800 nanoseconds. Okay. That's not bad. That's not bad. It's not horrible. Let's see. I guess I just like dimensions like that. Okay, so our thing is 64 by 16 by like, I don't know, 70. Tree points by the end, 1. Hmm. $256. Oh, yeah. I see. We can just add the cell size directly. This is the cell count. Now, if we had a cell count, that's how we would do it. Okay. Okay. Hold up. Dimensions. There's not a lot of data. 0.25. Let's see. Took 9 seconds. Okay. Take 51 milliseconds. Point interface dimensions return. Ith dimension. Okay. I'm gonna make this simpler because we don't need float 64s. We're not working with float 64s. So I'm gonna make a light volume point, which just has X, Y, and Z values that are float 32s. And we fulfill the point interface. And it also has beta, which is just light. Like that. And then it should be a color, I think. We'll see. Maybe it doesn't need to be a light color, a full color. So the point is an interface, so we have to have dimensions, which is 3. And then dimension I int, and it returns float 64. We say if I is equal to 0, return p.x. Y Z. Okay, so this is maybe a little bit better. So instead of this, we do this. That might be better because we're not making slices, so we're not accumulating extra data. X is X. Y is Y, Z is Z. For now, we're not going to do anything about the light color. Let's see how it goes. slightly better. If we don't have the light color, we're not working with that. It's roughly the same. Okay. What else can we do to make this faster? $65,536. We don't. Do we need it to be a pointer? That doesn't make it faster necessarily. I guess we could make this ahead of time, so we don't have to keep resizing the slice, because we know how many elements this is going to be. The capacity is going to be dim depth divided by cell size Z times this times that. So the depth, height, and then width. That doesn't make things better necessarily. When we make a new tree, it does directly take the points. Okay, so then we do need to pass it in. We do need to create new ones. Okay, this shouldn't be that slow. I mean, maybe that's fine. It feels like that could be faster. I don't know. 48 milliseconds, 46 milliseconds. That's not slow, but it just feels like it could be faster. But this might be fine. Okay. So we have our tree, and it has data. So now what we need to do is, when we go to render a model, we need to untransform the points so that the light... Well, actually, is it working? I don't think it is, actually. Yeah, it's not working, I don't think. Why isn't it working? Okay. Oh, is it because... Okay, on is set. We got the color, which actually we probably don't have a color of the overall light map. But that might be fine. Let's see. We don't need this anymore, I think. Resize. Okay, we're calling resize. This should light. This should be called here. Let's change the music. Beautiful. Beautiful. Okay, so we're calling light. We're calling light. We're supposed to be. Okay, so light volume is included here. It's missing method color. Missing method color. Light volume. New node. Oh. Not sure if I need to do that. Is that what I need to do? Camera. Light volume. Okay, cool. All right, so now I think it's working. Yeah, there we go. There we go. Ooh, it's bright. Yo, it might be working. Okay, well, it's not working yet, but we're almost there. Okay, so now what we need to do is we need to so we're resetting. I guess we'll leave that there. Well, no, that's fine. I guess what we want to do is we want to yeah, that's fine. I guess what we want to do is we want to get the, we don't need the normal. I guess we kind of do need the normal. We want to transform some kind of thing. We want to transform the positions of the points. We want to transform all of them by the inverse of the matrix of the model, so that we don't have to transform the models. I think. So we have models. We want to transform the points by the inverse. I'm thinking. I don't know if, I'm not sure if this is, not sure quite how I feel about this. I'm thinking. We need to transform the light volume. We need to transform the light volume, because if we don't transform the light volume, there's no way that we'll be like, hold on, let me break out a sprite so we can visualize this. Okay, well, let's do it on black background. So the idea is basically we have a cube, right? We have a cube like this. It is a three-dimensional cube, as you can see. And so we're dividing it up like this into pieces. We're dividing it up into pieces like this. And each cell is a point of light, essentially, or darkness, or whatever. Now, when we have a three-dimensional object, let's say this is the player, right? And so he's standing here. Rather than transforming each triangle of the player, we can just transform the matrix of the points by the inverse. so that basically it's like shifting the light volume by the inverse of the model, which is like shifting the model. It gives the same effect. That's faster because you don't, well, it would be faster if we didn't have to shift each individual point. If we do, then there's not much we can do about that. We kind of just have to do it. But we don't have to transform both. We only have to transform one, technically. Right? Let me think. Because the vertices here are untransformed. These are not the transformed vertices. So rather than transforming them again and transforming the model, the light volume, we could just transform the light volume's points by the inverse of the model's transformation and get the same result. Okay, I guess that kind of, yeah, because then you don't have to transform both, you only have to transform one. Let me think, is there another way we could do this? Is there another way we could do this? We have our object. No, I don't think it's possible. I think that we need to transform the points by some kind of matrix. So what would that even look like? Do we even need to do that though? Because we're only testing the positions of the KD tree of the grid. We're only testing the positions. So if we're only testing the positions, we have our character here. We're only testing the positions. Can we avoid transforming each point? Man, I feel like I'm close. I'm close, dude. I'm so close. There's a couple things that we would need to do to make this like really sing, but it's definitely possible. I'm thinking. I just gotta think. I just gotta think a little bit more. Because I don't want to have to transform each point. That's math. I don't think there's a way around it. I think I need to do that. Okay. So we don't have to transform the model, at least. The model can stay untransformed. We can instead get the inverse of the model's transformation. And then we can just... I guess I need a transformed version of the tree. Can I loop through the points and do that? Is this a copy or is this the original? I don't think that's well, if I'm keeping the points. Okay. This might be a copy. So what I can do if I'm keeping a pointer to these points, then I can manually transform them and keep an original. Okay. Like this. Like that. Like this. Okay. So original, we append the point. And then the active, we also, I guess we don't need to, hold on. Do I need 2 KD trees? Can I clone a KD tree? I can't. I can't. Okay, no, that's fine. So I modify the originals. Okay, I know what I need to do. Oh, I'm sorry. I'm bumping the microphone and stuff. All right, I think I know what I need to do. Here's what we're gonna do. We're gonna store the original and the active ones because we don't want to use the tree's points function because that's going to make a copy of the points. We don't need to make a copy. That's fine. We can just keep access the points directly like this. So we're storing the points. Then when we get here, we basically loop through the points and get the transformed version. This would be better if these were vectors directly. Then we wouldn't need to make another copy. Like this. Like that, and then X is X, Y is Z. So that we don't have to make another copy. Okay. So then we get the transformed version, which is p.position, or I guess inverse dot multivec p.position, and then we just I guess we'll get these are pointers, right? So p.position.x should be transformed x y z. Okay. So now this is an interesting concept. Now we can just because the color, the light volume itself doesn't even have a color because it is not a light in itself. Yeah. Yeah, there's no color here. It doesn't have color. Well, I guess it could have a color. That's fine, I guess. We can just do this. Okay, so now light factor R should be L dot KD, yeah, tree KNN. We need a point. Piece of no. Okay. K nearest neighbors. Let me think. Hold on. Make. Okay. I think what we can do here, we only need one. Well, it depends, but what we'll do is, I'm just thinking, man. Okay. So we want a KNN. Do we want? Okay, I'm gonna make a smaller. Oh, I guess you could use 0.3D for this purpose. Well, the thing about this is this represents float 64, so we don't want to allocate that. But I guess it's we could use this. Okay, so we can just say P is this, and then we can just say P 1. Yeah, I think maybe we need to be a pointer. Okay, so then we just set P.x to be vert pose x y z. Okay, so we are getting one result. Okay, so now let's get the first one, and we're gonna assume it is a light volume point. We want to get the light color, which is black. Okay, cool. All right. Print this out. We don't need the normal. We might need the normal. We might need the normal. We might need the normal. Okay. We might need the normal. No, we'll just do that. Ooh, it's that slow. Nah, dude, that is way too slow. Yeah. I'm gonna have to make maybe an alteration, because I think what's happening is this making a slice is bad. We don't want to do that. That's bad. So we're gonna probably make an alteration of this KD tree. The concept is there, but we don't want to make slice copies if we can help it. So let's make a fork. Cool. Okay, so yeah, what we want to do is I don't remember. Here we go, KNN. We can do a couple things, but one thing we can do is just straight up, well, we can just reuse the points. This might not work because we are operating on a single variable now rather than making new ones. Yeah, this entirely may not work because it's doing a lot of like slice stuff where it's just like copying slices and things, which is bad. All right, let's see what other options there are. Let's see. This, I wonder if I could use this by just maintaining 3 different interval trees. To access limits. Because then I can, does it doesn't seem like he's sorting these at all. Parse return slice with indices referencing input bounds. .3. Imagine input buttons index 11 with range 4.1 to 4.9, 10, 4.1. Same interval. Okay. So this could work actually. Almost no memory footprint. Okay. So I'm thinking that maybe I could do this. I could basically work with this where each cell is essentially two sides, right? Like the outer side and the left side and the right side, the top side, the down side, the forward side and the back side. Those are intervals. And I know exactly how big the intervals are. So I can create bounds for each cell and then pass in 3 different trees, including, well, I guess it'd be 3 different trees. And the intersection of them is the position of the does it have data? Can you store data? It gives you a result. The limits using in-tree bounds interface method to access limits. But there's no data, huh? But I guess input bounds. Oh, this allows you to get the bounds object. So the bounds object could have data. Okay. Okay, this could work. This could work. This could work. It's supposed to be fast. And this might be better because we don't have to, like, it should be, once it sorts, like, a KD tree, I don't know why my nose is weird, but a KD tree might be more than we need. Like this. A 3-dimensional KD tree. It says the first split, the red vertical plane, cuts the root cell into 2 subcells, each of which is then split by the green horizontal plane into 2 subcells. Finally, 4 cells are split by the 4 blue vertical plane into 2 subcells. So I'm wondering, like, it's a binary tree. Yeah, I'm wondering. Like, I'm wondering if we need a KD tree. It might be more complicated than we need. Because we might know, because we are splitting everything up into an even grid, it might be fine to just do an interval tree. So let's try that. Let's try it. Okay, so this is what it would look like. I'm gonna copy this. It's super simple. Okay. So this is still the same. This is roughly still the same, but we won't need this necessarily. So tree now is... Okay, so here's where we get the bounds. We put the bounds in. So the bounds... So I guess we have 3 trees. We have 3 trees here. So we have tree X, Y, and Z. Does it take it or it builds it? Okay, so I think it uses it so we can reuse the points. Okay, so the core concept here, oh, but wait, if the bounds... Where do we store the value? Where do we store the value? Okay, so I think we don't need the position, we just need the color. Okay, I think I got the general idea of what I'm thinking of. Hold up. Yeah. I think what we can do is we can get rid of this. I think we can make a... something like this. This is so wasteful, but I can't think of another way to do it. Shoot. Let's see. No, hold on. Where do I put the colors? That's the question. If I'm using intervals to get indices, we can get the limits. Basically, like, we can get the cell using 3 different tree tests on each axis. But once we have the cell, where do we put the color? Okay. Okay. I got it. This is gonna be a little wild. All right, so this is where we start off. What we want to do here is we want to. I guess we don't get to say points. Okay, so so the idea here, we want to append. Do we need to? Does it need to be? It does. Okay. Inbounds. Low is X, high is X. Okay. Yeah, it's just gonna be like that. Actually, I guess we could just do that, and then we could just combine CSX. Right, is minus CSX. Right. I mean, they're kind of the same thing. This might be a little easier to read. Okay, so this is the idea. Okay, So okay. Man, this is tough, dude. I think I got the general idea of what I'm trying to do. So we have 3 points. Let's just... Yeah, we can't even run it. We still need to transform that, but for now this is fine. I just want to see if it works. Oh yeah, it's not working. Okay, there we go. Okay, so this is working. All right, cool. So what I want to do is I want to see how much time does it take to construct this. Far faster. That's good. Okay. That makes sense because we don't care about paths. We're not trying to deal with paths and stuff. It's just intervals, and the intervals are all the same. Okay, so now what we can do, X, Y, Z. Now what we can do is we should be able to do this. For now, we won't worry about transforming the model. Yeah, for now. Okay, for now we won't worry about transforming the model. Let's just do this and see how it goes. Okay, so okay. So we don't need this. All right, so we're starting fresh. We're starting fresh, right? Yeah, everything's white. Everything's bright. Lighting, frame time is low. Okay, cool. So we're gonna probably end up transforming the vertices again, just for simplicity. Okay. So all right. Okay, so we have what I hope are transformed. Whoops. What I hope are transformed values. Okay, we're still doing pretty good. 60 FPS, and lighting frame time's high, but that's because we're printing out stuff. If we're not printing out stuff, I think we'll be okay. Okay, so what I want to do, the idea is we have 3 trees. We want to get basically the intervals that overlap. with these values. Like so. YZ, 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 OY, OZ. Let's see. Oops. Okay. So there are no inner overlaps on the y-axis for some of these triangles. That's impossible, right? Oh no. Yeah. There's some down here. All right. Fantastic. So now what we want to do is we want to say, oh, so it's overlapping on multiple triangles. Well, let's go back. So this is making slices, huh? Oops. It's not horrible. It's not horrible. It's not horrible yet. Like ideally we probably want to reuse the result. Let me see. Let's see. For length, STK is greater than 0. STK is NM. Val is less than or equal to NM. STK equals append LB. CN minus 1. Okay. All right. STK is. Trying to see like how many does this even call, like, is this recursive or I see this is this is recursive. Okay. All right, so I think we can make a modification that basically, like, it's stack. That's what it is. This is a stack. So we can make a modification that reuses the stack because we probably don't need to and would like not to make new slices all the time, but it's still working pretty well. It's still working pretty fast to the point where I think that this might be good enough to start with as a proof of concept. Let me do that. Yeah, this is not bad. It's not bad so far. Okay. So now that we have our intersection, we're gonna just grab the first one. We'll say if length OX is greater than 0 and length OY is greater than 0 and length OC is greater than 0, then X 0 C Y Z. So here's where we get a little crazy, because the index of these tree positions have to correspond in some way to the light values, the colors. Now, how do we do that though? I guess it doesn't matter as long as it's consistent, I think. So, yeah. So what we're going to do, we're going to say the color is light values index X plus index Y plus index Z. Okay, let's start off with that. Now it goes X left to right, X, and then Z is worth more. That is worth as much as index X could be. So basically dimensions, I guess we could just have a number of cells. Cell num X int Y Z. So then when we do this, we can count like this. See? Let's do it like that. Plus plus. Plus plus. Plus plus. And then we just say L.cell num X equals cell X T Z Y. Okay. So then we just say times cell num Y X Z. All right, that's the idea. That's the idea. And we can just underscore this color. It's fine. All right. Okay. I'm not really sure why lighting frame time is lower now than before. Interesting. Okay, so I think that this should work. What we now need to do is I'll do it right here. All right, and then we just multiply this by color. Okay, so something like that. So there's, yeah, this is basically it, right? There's no change essentially. So now what we want to do, we probably want to make some functions to write to the volume. Okay, so position takes a vector 3, color takes a color. The concept is the same as this. We know it's not skinned because we're writing the position manually, so, and we don't have a normal. So instead it's position equals, we don't have to transform because it's already been transformed. So ostensibly. So then we're just passing in the position manually. If we have a result, then we then write to the light values thusly. I guess we just do like this. There we go. Cool. So this is a write. And I guess we can make a read. Okay. We can use alpha to indicate. Yeah, cool. All right. Or no. Here is what I'm looking. Yeah. Okay, we can use alpha 0. Yeah. All right. So this should be working. All right. So if it's working, then we should be able to say light map dot write. You know what? Let's make a helper function. We're going to make this write color to position, read color from position, and then we'll make a helper function. For each position, write. That basically does this, but for every possible position. I think. Let's see. Okay, so I'm just like drum and bass, just like I think this just brain just moving, dude. So this is actually just this. We just want to loop through this. Yeah, we just want to loop through this with dim instead being L.dimensions. Because it does have dimensions. Okay. Do we actually write that anywhere? Do we actually set that? I don't think we do. L.dimensions. Dimensions. Okay. So now down here, we loop through like this. Cell size X. How do we do it? We did it in what order here? We didn't do it in any specific order. Well, ZYX, but that's not necessary. Okay. So, yeah, I guess we're just good to do it in... We'll do it in reverse order. Okay. So now we do this. We're passing in X, Y, and Z manually. And then when we get a result, we then for each func, it's a color in out. We'll do it like that. Okay, so for each, we call it in, and then we set it to be out. Whoo! Okay. So then this is really just a for each, right? Because you can read it within, and then you can just, yeah. So for each position, read right. All right. Okay, let's see if this at all works, dude. All right. Okay, so this is working. I mean, yeah, we're not really doing anything, but it's doing stuff. It's rendering like normal. So if this works, then we should be able to say light map dot for each position read write. And we pass a function and we return in. Or we could say out equals in, either one. So if we just do that, no change. But we could say if, oh no, that's right. I wanted to get the position. That's right. Okay. So then it would be, because there in would not be even a color, right? No, you might want to read it. Yeah. It could be pre-calculated. Okay. So position would be a vector 3, and then we have in. Position is going to be, I don't even know if it's possible to avoid allocating a new vector 3 for this each turn, but we'll just do it like that. X, Y, Z. So we don't have to do that. Just do it like that. So now what I'm envisioning is to say in if position dot x is greater than 0, in dot r equals 1. Ain't no way. Yo, this works. This works. Hold up. This is hold up. Hold up. This might be working. Let me see. If x is greater than 0, so that should be these triangles or these vertices here, right? Because this x is, oh wait, oh no, this is the center point. Oh yeah, that's true. Okay, hold up. Well, no, wait. The mesh is what the mesh is. This is it's yeah, okay. So from this point, x should be, yeah, all of these. So it's not quite perfect, but it is pretty close. There's a definite line here, but then it kind of cuts off down here. Oh no, wait, that's right, because it might be working, because the volume doesn't extend all the way down. We make it bigger like that. Ooh. Okay. So the whole point of this Yeah, I'm so close, dude. Hold on, let me think. Okay. This is still really cool. This is still really cool. I'm just trying to figure out exactly how do I use this. So if I... let me destroy this, man. Okay. So, is it working? Yeah, I think it is. I think it actually is. Everything on this side is red. That's crazy. Yeah, I think it's working. So, what we can do... What we can do is maybe something cool like this. Okay, so I chopped off the top part of the top floor. And so what I want to do is maybe do something like... Let me think. Okay, I think I have an idea of what I could do with this now. So we're gonna do a collision test. We're gonna pass in the position. We're gonna pass a radius of 0.25. And we're gonna test against everything. And it does return first collision found. Oh yeah. Okay. Subtractive. It's true. Okay. All right. Okay, let's see. Let's see. The default is black, right? We filled on resize, it's filled with 0, yeah. Okay, subtractive. Okay. Right. Okay. Well, wait, with subtractive being true, why is it right? Cell color subtractive. Maybe we have to do that. Oh, I see. I guess actually it's probably best like this. Times are really multiplicative would be better. Okay. So cool. So what let me see. It's multiplicative. Times 1. Yeah, these are all 0. So then why is it darker? If we don't do anything, that's what it looks like. If we do this, this is what it looks like. But why? We're not... Only red. R. Oh, times equals 0. Oh, that's why. That makes sense. We will really, I guess, want subtractive. Okay, so I think if I'm doing this right, then we can go here and we can say, give us a triangle mesh. Okay. Let's see. Make it more specific. So there's a little bit there. There's a little bit there. There's a little bit there. What if we make the sphere smaller? We make the sphere much smaller. Collided. Okay, hold up. We might be kind of getting there. Collision test sphere. I feel like this shouldn't be colliding. Collision test sphere. Position and radius. Touch this part? Hmm. Two. Oh, well, maybe the cell size is too large. Let's make the cell size something bigger. Maybe smaller? Interesting. Very interesting indeed. Oh, I'm sorry. I keep forgetting to do that. This is interesting. This is interesting. Lighting frame time is pretty good. But the potential is super high because you might be like, what's the big deal? Kind of. The big deal is that this is dynamic lighting. It's actually dynamic. The light map or the light volume is dynamic. So like, if we say g.scene add children cube, new cube, new model. It would be camera. We add a cube camera. Okay, so here's an example. So it's a cube that's in front of the camera, and as we move into the darkness, it gets dark too. This is wild, dude. This is crazy. That's crazy. That's crazy. That's crazy, dude. That's wild. That's so cool. That's so cool. It's such a vibe. It's so cool, dude. Like that's incredible. So it's like there's shadow and stuff. That's crazy. And it gets lighter and oh man, this is bananas, man. This is actually insane. I need to like refine it, but the potential is so incredibly high. It's crazy how much potential there is here. Okay, here's an example. Here's an example I think that I could probably use to make this more visible, more obvious. Instead of this, we're gonna do this. We're gonna say if ray test from position to position dot add 0 add y 1000. In dot r equals 1 g b. Oh, I didn't like. Let's see. Do I want to panic if options test against? Well, I guess that we could just return no. That's valid. Cool. So test against is scene. It's so cool, dude. So it's like, oh, dude, this is so cool. So yeah, let me up the cell size. Ooh, this is so cool. This is dope. This is dope, dude. Let me make it like that. Let me go over here. Let me add a sun lamp. We're gonna tweak it like this. We're gonna remove these. We're going to rotate it like that. We're gonna make it a little brighter. We're going to save. Oh, dude, this is this is so cool. This is so cool. Hold up. You're gonna, this is crazy, dude. Examples, light map. And then give me the baking. Yeah, okay. Grab these. Let's see. I guess we can just bake the thing in here. Hold up, let's see. Oh, is that hold up, let me see. Light map. GLB. Does it have to be GLB? Oh yeah, plus bin, plus external. Oh no. Yeah, that should pack the textures. Let's see. Pack. Load external textures. Pack textures. Okay. So then, let's see. Brother. Hold up. This broke at some point and I didn't realize it. Oh, yeah. Let me change the music. TF. Let's see. What's up with the textures? Export unused textures. Uh, something up with the textures not exporting. Okay, let's see something real quick because it says it's supposed to be exporting, but I don't see anything. So let's try this. Hmm? Oh, maybe it has to be this one. Maybe this is what it needs to be, that. Yeah, okay, that's what it was. That was my bad. Okay, I think that should do it. Don't need the GLTF anymore. Or the bin. Or the palette stuff. Okay. Okay, hold up. This is dangerously close to becoming peak. This is dangerously close. All right, so undo that. Okay, so we're doing a ray test. All right, let's see, from to. I think I'm on the right track, but I think, yeah, this should be, well, I guess there's an easier way to tell. We can just do something like this. Let's do it like that. Yeah. The potential is crazy here, dude. So, okay. There's something going on where I think position that, like, we're doing ray tests, but I think it's not. Oh yeah, okay, yeah. That I'm sorry. That I just my brain was like click, click, click. I remember now. Yeah, this is the issue. Okay, we have to transform these positions. We have to transform these positions. L dot node transform Wolfbeck. Yeah, and then from model should do this. And then the node transform set world transform model.transform. That should help. Closer-ish? Closer-ish. Closer-ish. Let's see. We're setting the world transform. We probably should transform the dimensions. Yeah, I think we have to transform the dimensions. We're trying not to transform the dimensions. Okay, we're trying not to transform the dimensions. Trying not to transform the dimensions. We have to transform the dimensions. Okay. No, they are already transformed. Okay. So then we transform the model. Transform. Oh, well, this is already transformed. We don't have to transform it again. Oh, then yeah, that's not the problem. Although I think I'm on the right track. I think it does have to do with transformations and stuff. Like, this is cool. Like, let me do this. Like, the potential, dude. Like, once I get this working, there will be shadows and stuff. It's gonna be crazy. But vertex-based shadows, it's gonna be so, like, weird and low poly, and it's gonna be crazy, dude. Like, I think the problem is with the transformation of the vertices, of the positions and stuff. Yeah, I think the issue here. I think there's multiple issues. I think one might be the transformation. I think this is also not indexing the light values correctly. For each position, read right. Already transformed. The dimensions min, max, z. Oh, well, that's not. Like, that's not. It ain't helping. That ain't helping. ZYX, 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 Z equals Z plus equal. OG tree XYZ, including XYZ, oh, XYZ. Index XYZ. Cell num X, cell num index Z, cell num X, cell num Z. I'm so close, dude. I'm like, I think I'm like super duper close. Because which colors correspond to which cells is determined, like, like we determine that. We determine how to index the light values. So let me go back. Let me go back and just say oops. There we go. Let's see. So like split right down the middle. Is that how it is here? Yeah. This is world position 10. Yeah, that's 0. This is 0 right here, this green line. So then, okay, let's see. Yeah, okay. All right, I shifted it to the right. So now the wall is dark. See, that's cool. That's very cool. But you see, this makes me think maybe it's something else, because like depending on like the angle, how visible it is changes. If I'm like here, it's like almost unseeable. So that implies there's an issue here. Model transform. We don't even need to transform the vertex normals technically. Let's see, model transform, and we're multiplying the vertex positions of the model's mesh. XZ. Oh, wait. X, Y is X, Z is Y, X and Y. Oh, yeah, that might be it. Yeah. Okay, so let's make, I think that's the bug. We're gonna make a function for this. And then we're gonna make another one for set. like that. So yeah, let's say get my value. Okay, let's see. Get the 0, y0, OZ0, set 0, y0, OZ0. That might help. Not quite. It's way darker depending on facing, which is not correct. Yeah, it's definitely not correct. But I think I'm on the right track. Did I actually fix it, or did I... X, Y times X, Z... Oh, wait. X plus... Because the way I'm envisioning it, and I gotta get going, but the way I'm envisioning it is basically these positions, which, you know, are in three-dimensional space, you know, different all the way through, they become basically a flat array like this. They become a flat list. And so we have like 1, 2, 3, 4, 5, etc., right? And so this is a flat list that's compressed. The concept is the same as like a tile map. So all the X values and Y values and Z values that comprise a single cell of this volume corresponds to different values. So for example, X ranges from 0 to let's say 100, right? Let's say Y does the same thing. It ranges from 0 to 100, but each Y value is worth 100 X values. So this basically, let's say an X, Y, and Z of 0, all, you know, 0, 0, 0, that's position 0 in the array. And so the first 100 are X 100, right? 0 to 100. But then the next 100 are X 0 to 100 plus Y times X 0 to 100 plus Y times a cell, the number of cells. So the index of 1 would be 100 plus 0, 1, etc. And then Z should be X times Y times index Z. That feels like that's correct. Yeah, that feels correct. I feel like everything here is... Yeah, it's the same. Well, I feel like I'm super duper uber close to getting this to work. But alas, I may not be able to do everything that I wanted to do. Points, tree Z, new entry. Cell count. Is the cell count working correctly? Z, Y. Cell count X plus. I think that should work. I think that's correct. Let's see. $64, 20, 64. That sounds correct because it's a flat cube. Okay, so the numbers should be, whoops, the numbers should be correct. The bounds should be correct. These are transformed dimensions, right? Dimensions are transformed. Yeah, they're already transformed. Why do I even have a node? Oh, that's right, yeah. For each vertex index, transform. Man, I'm so close, dude. I feel like I'm like super duper close because this is so what's the word? It's so promising. So promising. Yeah, like under here, they should be darker. Oh no, wait. It's, yeah, position X is greater than 10. That's, whoops, that's still an issue though. I'm all over the map. Yeah, this still is a problem. Like, that is correct, but once I'm in the darkness, as I turn around, it gets lighter. Like, it should never get lighter. Yeah, like it's just bright all the time. That's so cool. If I could get it to work, this would be bananas, dude. But why is it unaltered? Transform Multvec. Close, dude. I'm so close. Transform Multvec. Vertex positions. Get value. I'm so close, dude. Like I keep saying that because I'm so close. I'm so close. It's just barely off. It's just barely off. But like when I get it to work, brother, it's gonna be absurd. It's gonna be crazy. It's gonna be crazy to have like real-time lighting. kind of. Kind of real-time lighting. Anyway, I'm gonna stop here. I got stuff to do. Thank you very much for watching. I've been Solar Loon. It's been real. I'll catch you guys on the flip side next time, and I hope to get an update for Master Plan out real soon. Yeah, that's literally just have to push it out. But yeah, thanks for watching. If you want to check out this stream or more streams or whatever, check out my YouTube channel. youtube.com/SolarLoonTube, I believe it is, or I think it's just SolarLoon actually. Check out github.com/SolarLoon. Check out itch.io/SolarLoon, and I appreciate it. All right, I'll catch you guys on the flip side. See ya.